We look now at the instructions that a CPU can understand.
Understand is an extremely generous word. Most people would say a CPU is the fastest laborer that has no idea what it is doing.
In the von Neumann architecture, the CPU fetches instructions from memory and executes them repeatedly, regardless of whether this is part of an instruction for sending an email, computing a trajectory, solving analytically an equation, or drawing a picture on a screen.
So much is the CPU unaware of the purpose of the code that it is running, that such code could be a computer virus.
Since data is the same as instructions, both are sequences of zeros and ones, the CPU may be accidentally executing data that was not meant to be treated as instructions.
Nevertheless, a CPU is designed to operate on a set of instructions. Programmers, or tools that generate code for the CPU, such as compilers, are supposed to use this set of instructions meaningfully.
The set of instructions designed for a CPU are an instruction set architecture, or ISA, because we may implement the same set of instructions by different, typically faster or more energy-efficient hardware, and the software already designed would not require to change.
That is, the ISA provides a level of abstraction. The code does not have to be concerned with exactly how the hardware works.
To illustrate an ISA, we will use the MIPS.
This is a 32-bit RISC architecture. That is, memory words are 32 bits.
Although the addressable memory usually has 2 to the 30 words, the CPU only has 32 registers with the capacity of 1 word each.
Registers are numbered, and because of their purpose they are classified when referring to them in assembler.
Register $T0 in assembler is in fact register number 8, register $T1 is register number 9, and so on until register $T7 is register 15.
Registers $T8 and $T9 are registers number 24 and 25.
Registers $S0 to $S7 are registers numbered from 16 to 23.
When we look at subroutines we will see the T is for registers that hold temporary values, while those named S is for those that are placed on the stack.
The first format of the ISA of MIPS for an instruction is the R format.
In the 32 bits of a word, the first 6 bits are the operation code, or opcode.
The fetch brings into the instruction register the instruction from the place in RAM pointed by the program counter.
The decoding of the opcode happens in MIPS analyzing the 6 bits of the opcode in the instruction register.
The next part of a R formatted instruction are the numbers of 3 registers.
Note that with 5 bits we can specify one of the 32 registers.
Thus, an assembler instruction such as add $T2, $T3, $T4 corresponds to an opcode of 6 zeros, the binary for 10. The register $T2 is the 10th register, the binary for 11, the name of $T3, and the binary for 12, the name of the register $T4.
MIPS addresses are made of 32 bits as well, but an address refers to a byte, the fourth part of a word.
While one can consider the memory as a large array of bytes, in MIPS one can consider the RAM a large array of words, but the next address has an increment of 4.
MIPS uses little endian, meaning that the bytes inside a word are packed so that the fourth byte occupies the most significant byte of a word.
For example, if in the data section, indicated by the directive .data, we specify the string hello using the directive .ASCII, Z, then the first byte, the ASCII for H, would be in the least significant byte, while the byte for the second L would be in the highest position of the first word.
Nevertheless, using programs to produce programs is one of the most useful things computers do.
That is, computers treat instructions as data, and in machine learning, they autonomously build programs.